In this lecture, I'm going to be talking about Ampere's law. There's a parallel between Ampere's law and using it for calculating magnetic field and using Gauss's law to calculate electric field. So I'm going to write down what that parallel looks like first. Gauss's law for electric field. What does it do? It relates the electric field on a closed surface to the net charge enclosed by that surface. Okay, so it gives us a relationship between the net charge enclosed by the surface and the electric field on that closed surface. Ampere's law is very similar. What it does is it relates the magnetic field on a closed, and this time instead of a surface, it's a path. And I'll get into more details about what that is. And it relates it to not the net charge, but the net current that passes through that path. Okay, so you can see the similarities. They're used in very similar ways, but there's some important differences. One of them that I want to point out right now is that in this one, we're talking about a closed surface. So that's a two-dimensional surface. So when we were doing calculations with Gauss's law, we saw that the surface area would appear in the calculation because we're talking about a surface. Here, now we're talking about a path, which is a one-dimensional line. And so what we'll see is we'll be finding the circumference or the perimeter in our calculations. Okay, so that's a very important difference. It's easy to get the formulas confused as far as surface area versus circumference, so be careful. And then closed surface means that the surface has no holes in it, effectively. A closed path, you could say it's a path with no holes, but what it is it's a path that returns to the point where it started. So it's a complete loop, although it doesn't have to be shaped like a circle, but it's a complete loop. Okay, so now I'm just going to write down Ampere's law. So what does it look like? So we're taking an integral, this time of the magnetic field instead of the electric field, and we're taking that integral over a closed path instead of over a closed surface. And that path is going to be parameterized by little vectors dl that point along the path in the direction that we're traversing the path. So I'm going to get into more detail about what that's all about. And that equals mu naught, physical constant, times the net current that passes through this path. And I'll talk about what it means for it to pass through the path as well. So this is Ampere's law. All right, and this closed path, the size and shape of the path don't matter. And I'll refer you to your textbook for explanations as to why. But we can use any shape and any size path, and this equation is true. So we should use a path, we should choose one that is convenient, and we'll see a couple examples of that. So the size and shape of this path doesn't matter as long as it's a closed path. Okay, and then I want to point out another parallel between this and Gauss's law. So with Gauss's law, remember that any charge that appeared outside the surface, outside of the closed surface, did not contribute to the flux through the surface. And remember, to find the flux through the surface, we were integrating over the surface, so we call that a surface integral. We were integrating E.dA everywhere over the surface. And so charge that is outside of the surface does not affect the surface integral. Ampere's law has a similar property, except now it's current that's outside the closed path, meaning it does not travel through the path, it doesn't pierce the surface defined by the path, and I'll talk more about that in a minute. That doesn't contribute to the, now we're not doing a surface integral, we're doing what's called a path integral because we're integrating along a path. So that does not contribute to the path integral if the current is outside the closed path. All right, so now I'm going to give you a step-by-step recipe for using Ampere's law, and this is also found in your textbook. So step one is to choose a closed path. Again, you might as well choose one that's convenient, and I'll give you a couple of examples of that. Step two, as your book describes it, is to stretch a soap bubble across the path. So what this means is we're imagining that this path, say it's a circular loop, has a surface inside of it. Okay, so this is a surface where the path is the boundary of the surface. And it turns out that this surface can have any shape, just like the path, the surface can have any shape and it still works. So here I've tried to draw that. I don't know if this drawing makes any sense, but the soap bubble doesn't have to stretch flat across this. It can bulge. This looks kind of like a basket. And so the surface doesn't matter as long as the border of that surface is defined by our closed path. Okay, and the proof for this is it's a mathematical theorem that we'll have to say for another day. All right, moving on to step three. Okay, so we defined our path, and we stretched a soap bubble over the path, and now we're going to walk around the path. And I'm going to put walk in quotes because no one's literally walking around the path, but it's helpful to think of it like that, to think that we are traversing this path. And we're going to traverse the path in the counterclockwise direction, just as a general rule of thumb. And our reason for walking around this path is because that allows us to calculate the path integral, which is the left-hand side of Ampere's law. So we're going to calculate this integral by walking around the path counterclockwise. And at every point, taking the dot product between the magnetic field and dl. dl is a vector pointing in the direction we are walking. All right, step four is to find that net current, which is by adding up the positive and negative currents. And I'll talk about what makes one positive and one negative. Adding up the positive and negative currents that pierce the soap bubble, the imaginary soap bubble that we've stretched across our path. Okay, and so what determines whether the current is positive or negative? For this, I'm going to use a modified version of right-hand rule number 2. And remember, right-hand rule number 2 is the one where you take your right hand, you curl your fingers in the direction of the magnetic field, and your thumb points in the direction of the current that's creating that magnetic field. Okay. In this case, we're going to curl our fingers in the direction of the magnetic field. And now our thumb points in the direction of positive current. Okay, so basically we're choosing the sign convention so that the right-hand rule still holds. Okay, and once we've done that, we've calculated the left-hand side, we've calculated the right-hand side. The left-hand side was calculated in step 3. The right-hand side was calculated in step 4. And now we plug those in to Ampere's law by equating left-hand side and right-hand side. And then solve for the unknown. And typically the unknown is going to be B, but it doesn't have to be. All right, now I'm going to do a couple of examples of applying Ampere's law. And so we'll see a lot of these ideas in action here. So the first example I want to do is the magnetic field due to a long straight wire. So this is something that we've calculated before in a previous chapter. And so we know what the result should be. So we're going to verify that Ampere's law agrees with the result that we calculated before using the Biot-Savart law. And that result was mu naught over 4 pi 2 times the current over r, which is the distance from the current. Right, that's the magnetic field strength due to a long straight wire that's carrying a current I. So I can draw this in a number of different ways. I'm going to go ahead and draw it with current coming out of the page. Okay, and I'm going to draw my Amperian loop. Right, in Gauss's law, we were doing a Gaussian surface. Now, with Ampere's law, we're doing an Amperian loop. And I'm just going to make it a circle that has I at the center. Okay, now we know that the magnetic field due to I is going to point counterclockwise around this circle because we can use right-hand rule number 2. I point my thumb in the direction of current, so it comes out of the page, and my fingers curl in the direction of the magnetic field. So we know that B goes around this way, around our Amperian loop. Okay. So like when we were doing Gauss's law, we typically made use of something that we already knew about the electric field. And we're doing the same thing here with Ampere's law and the magnetic field. We already know that the magnetic field is going to go counterclockwise around this. And another thing that we know, and this is an argument based on symmetry. We don't need this equation yet, although this equation also tells us this. But just based on symmetry, since B at all points along the circle are the same distance from the current, then we can assume that B must be constant along this circle because all these points are equidistant from the current. Okay, now, what direction are we walking? Remember, we walk counterclockwise around this loop. So when I walk counterclockwise around this loop, what does DL look like? And remember, DL is a little vector, an infinitesimally small vector, that at each point is pointing in the direction we're walking. So as we're going counterclockwise around this loop, I'll draw it next to this. DL is also always going to be pointing counterclockwise around this loop. DL and B are always going to be in the same direction. They're both traversing the loop in a counterclockwise direction. B goes around counterclockwise, and we are quote unquote walking around the loop counterclockwise. And so from this, we can see that B is parallel to DL. And so when we take the dot product, B dot DL, which is what appears inside our integral, it equals B, the magnitude of B, times the magnitude of DL, times the cosine of the angle between them, but the angle between them is 0, and the cosine of 0 is 1. Okay, so inside our integral, B dot DL just becomes B times DL. Magnitude times the magnitude of scalar times the scalar. And I argued that B is constant along the loop, so as we walk around this loop, the circle, remember, reminds us that we're walking around a closed loop. B is constant, so that means I can pull it out of the integral. And now I have the integral of DL going around a loop. Well, this is going to be the circumference of the loop, because we're adding up little lengths, and we're doing that all the way around the loop. And so by the time we do that, we've added up the entire length of the loop. So this integral becomes the circumference, or the length of our path. And so what is that? Well, it's a circle. Okay, so the circumference of the circle is 2 pi r. And this is the part where you need to be careful. We're talking about a circumference here, not an area. Okay, so r should not be squared. Okay, so that was steps 1, 2, and 3. Now step 4 is how much current pierces the soap bubble that we stretch across our path here. So you can imagine a soap bubble that's stretched across this path. Like this path is a hoop, and there's a soap bubble in the hoop. Only I passes through that soap bubble. Only I pierces it. What's the sign of I? So remember our sign convention was I'm going to curl my fingers in the direction of B, and my thumb points in the direction of I. Right, so it's a modified version of right-hand rule number 2. Basically, we're choosing the sign of I so that right-hand rule number 2 is followed. Okay, so I here is positive. So I net then piercing the soap bubble is just positive I. All right, and then the last step, step 5, is to put it together. Take our left-hand side, which we calculated was B 2 pi r, and that's equal to mu naught times the net current passing through. All right, and then I'm going to solve this for B. And now if you compare that to the formula we were expecting, you can see that these are the same if I take this one and multiply it by 2 over 2, right? Which is not going to change anything because I'm just multiplying by 1. But if I multiply this by 2 over 2, then I get mu naught over 4 pi times 2I over r as expected. And why did we multiply by 2 over 2? Why didn't we just leave it like this? And that's because, remember, mu naught over 4 pi is a number that we know. And moreover, this is a very simple number. Remember, this number is just equal to 10 to the minus 7. So the reason for multiplying by the 2 over 2 is to put a simple known number into our formula to make life easier in the future when we're doing this calculation. Okay, so Ampere's law checks out compared to what we already knew from using the Biot-Savart law. And this calculation was much easier than the one that we did using the Biot-Savart law. All right, now I'm going to do example number 2. And for example number 2, I'm going to do the magnetic field due to a solenoid. And remember, a solenoid is a wire that's coiled around a cylinder. And again, we have an expected result here. We know from using Biot-Savart law earlier that it should look like this, mu naught n I over L. And let me explain what each of these variables means. First, I'm going to draw my solenoid. Okay, so here's my cylinder with a wire coiled around it. The length of the cylinder is L that we see in the formula. And N is the number of coils, how many times this is wrapped. There's a number of coils. And then I is the current that's going through the wire. And we need to pick a direction for I. So I'm just going to pick one for the purposes of this example to be going this direction. So when it's on the near side of the cylinder, it's going down. And then below the cylinder, it's going into the page. Behind the cylinder, it's going up. And then at the top of the cylinder, it's coming out of the page and then going down. Okay, so it's going to do that all the way around. And again, we're going to use some prior knowledge here. Right-hand rule number 3 tells us the direction of the magnetic field due to this coil. And so remember, right-hand rule number 3 was curl your fingers in the direction of I and your thumb points in the direction of the magnetic field. So the B field should be to the right inside the coil, which means that since it wraps around and comes back in the other end, then outside the coil, it's going to be going to the left, both above and below. The magnetic field is going to the left. But inside the coil, it's going to the right. We also saw that the magnetic field above and below the coil, outside the coil, is very small. Okay, so we're going to take advantage of that knowledge as well. So now I'm going to draw my Amperian loop. And whereas last time it was convenient to draw it as a circle, this time it'll be convenient to draw our Amperian loop as a rectangle. And we'll see why once we get into the integral. And where are we calculating b? We're calculating b inside the coil. Okay, that's what this formula tells us. B inside the coil. And that's why this rectangular loop goes inside the coil here. That's where I'm going to be trying to find or calculate b. So we need to make sure that our loop incorporates the location where we want to know b. All right, so that's a 3D drawing. I'm going to now do a 2D drawing. I'm going to imagine I'm taking a cutaway view where I'm slicing this coil along the page, along the paper. And so when the current is either coming out or going into the paper, it's coming out up here, going in down here. So that's how I'm going to draw it. And I'm just going to focus on the part that's inside my rectangle. So all of these currents are coming out of the paper. Okay, so I'm going to draw them like this. Okay, and my rectangular Amperian loop goes around like this. And then I have more currents here, more currents here. And this is, up here is outside the coil. Down here is inside the coil. And then we have all the currents that are going into the page are going to be down here as well, but they're outside of my loop, right? So they do not affect my path integral. So I'm only concerned about the ones that are inside my rectangular Amperian loop. Okay, so we've already used right-hand rule number 3 to note that the magnetic field points to the right inside the coil, and it points to the left outside the coil. And outside the coil, it's very small, so this is close to 0. And what's it doing on these parts of the loop? Well, it depends on whether we're inside or outside the coil. Everywhere inside the coil, the magnetic field is to the right. So there and there. That's what the magnetic field looks like. And outside the coil, it's everywhere to the left. Okay. And now we're going to compute the integral by walking around this path in a counterclockwise direction. So I need to do this part of the rectangle plus this part plus this part plus that part. And that would be my path integral around this loop. And before I do this, let me give this rectangle a size. Let's say that it is length d. Okay. The height is going to turn out to be irrelevant, although we could define that if we wanted to, but it's going to not matter. So what is the path integral, the piece of the path integral along here? Well, b is constant everywhere inside the loop. So b is constant all along here. And so it's just going to be b times this length. And this length is d. So integral of b dot dl. Oh, and what's the direction of dl? Remember, we're walking counterclockwise around this loop. So dl goes that way. And then over here, it goes that way. And up here, it goes this way. Right? We're going counterclockwise around this loop when we compute the integral. Okay? So along here, b and dl are in the same direction. So so theta is 0 and cosine of 0 is 1. So we're going to get b dl. I'm sorry, bd, right? This length is d. dl is an infinitesimal one that we're integrating to get d. Here, notice that dl is everywhere perpendicular to b, right? B is to the right or is to the left, and dl is up. So b dot dl here is 0. So b dot dl down here was bd. Over here it's 0. Up here, we're approximating B is approximately 0, so so B times dl is just 0 up here. And over here, again, dl is perpendicular to B, so plus 0. Okay, so the left-hand side, the path integral just becomes BD. And this is why we chose a rectangular loop. It's because this perpendicular part and this perpendicular part of the loop don't contribute to the path integral. It makes the math easier, right? They contribute 0. Okay, that was step 3. Now step 4 is to find how much current pierces the soap bubble that we stretch across this rectangle. So each of these wires carries a current I. And is it positive I or negative I? So I'm going to take my fingers, I'm going to go in the direction of B, which is, for a single wire, is around a circle like this, right? And you can see my B is more or less counterclockwise. It's to the right down here, and it's to the left up here. And my thumb is pointing out of the page, so these are all positive currents by our sign convention. These are all positive. So the real question then is, how many are there? And so to do that, to figure that out, it's going to depend on the length of our rectangle, right? So how many currents pierce the soap bubble? It depends on D. A wider rectangle is going to enclose more currents than a narrower one. So the way that we're going to figure this out is by noting that we know that there's N coils, and we're assuming they're evenly distributed along this length. And so we know that if it's a length L, that N over L tells us how many coils per length we have in this solenoid. So N over L is equal to the number of coils per length. And so the number that would fit inside our rectangle would be the number per length times the length of the rectangle. Okay, so the number inside is equal to the number per length times the length of our rectangle, which I called D. All right, and so that's how many currents, and each current, or each wire that pierces the soap bubble is carrying a current plus I. So I net is going to be positive I times this many, right? I've got this many currents piercing the soap bubble, so it's going to be I times this, so N D over L. All right, that was step 4. Last step, step 5, is to equate the left-hand side and the right-hand side. So the left-hand side was this integral, which evaluated to BD. Okay, so we're using Ampere's law now. The right-hand side is mu naught times I net, which is I N D over L. And notice that the D's cancel. And I mentioned this back with Gauss's law too. The D has to cancel. If it doesn't, we did something wrong. And the reason for that is because D is an imaginary mathematical, it's the length of this imaginary mathematical loop that we created. And the laws of nature are not going to care about which size of imaginary loop we chose when we were doing this calculation. Okay, they need to be independent of the imaginary part. So you can see that we're left with B equals mu naught I N over L, which is what we were expecting. Okay, so Ampere's law checks out for the solenoid as well. And again, this is a simpler, much simpler calculation than using the Biot-Savart law.